I'm excited to announce today that Dr. Michael Gion and his team have used our Spitzer Space Telescope to determine that there are actually 7 Earth-sized planets orbiting the nearby TRAPPIST-1 star about 40 light years away. What's more, as you can see in this illustration, is that 3 of these planets, marked in green, are in the habitable zone, where liquid water can pool on the surface. In fact, with the right atmospheric conditions, there could be water on any of these planets. So for the first time, we found as many terrestrial planets around a single star, and that's the first time we have been able to measure, in addition to that, both the masses and the radii of these habitable zone type Earth-sized planets. These planets are among the best of all the planets we know to follow up, to see, for example, with the James Webb Space Telescope that we're going to launch last year, the atmospheres, and also to look at biosignatures if there are any. The discovery gives us a hint that finding a second Earth is not just a matter of if, but when. Scientists believe, actually, that around every star there could be 1 planet. Take 3, take 5, take 7. And you can just imagine how many worlds are out there that have a shot to becoming a habitable ecosystem that we could explore. And what we really have in this story is a major step forward towards answering one of these very questions that are at the heart of so many of our philosophers, of what we're thinking about when we're by ourselves. And that basically is, are we alone out there? We're making a step forward with this, a leap forward, in fact, towards answering that question.
Around the same star, not 1, not 2, but 7 Earth-sized planets. And this is the first time that so many Earth-sized planets are found around the same star. Furthermore, with 3 of them in the habitable zone. And the star itself is what is called an ultra-cool dwarf, which is the least massive kind of stars that exist. And these stars are much smaller, much cooler than our Sun. And still, they are very frequent at the scale of our galaxy, more frequent than solar-type stars. And if you look at this illustration, you see the comparison between a basketball and a golf ball. Well, in our case, the basketball would be the Sun, and the golf ball, it would be TRAPPIST-1. So TRAPPIST-1 is much cooler, much smaller than our Sun, and so the planets in its habitable zone are much closer to it, very close to it, with very short orbital periods. And in this graphics, what you can see are the planets which were found around TRAPPIST-1, with the 3 of them which are in the habitable zone, so also called the Goldilocks zones, where liquid water could exist, is the most likely to exist at the surface of a rocky planet. Having 3 of these Earth-sized planets in this habitable zone is very promising for the search for life beyond our solar system. And furthermore, we have, thanks to Spitzer 2, preliminary measurements of the masses for 6 of them. And for 1 of them, our measurement is precise enough to strongly suggest a water-rich composition, which is very exciting because this is one of the planets in the habitable zone. Furthermore, these planets are orbiting so close to the star that they must be, or they are probably, tidally locked, which means they always face the star with the same side, like the Moon to the Earth. And so if you look at this animation, you can see a view of tidally locked planet with a permanent day side and a permanent night side. The TRAPPIST-1 planet could be just like this. Now, what is also exciting here about this system is that the planets are so close to each other. If you were on the surface of one of these planets, you would have a wonderful view on the other planets. You wouldn't see them like we see Venus or Mars, like dots of light. But as you can see in the next illustration, you would see them really as we see the Moon. You would see worlds with, which are very big. You could see the structures on these worlds. They would be as large as the Moon and even larger for some of them. So it would be a wonderful view on these planets.
In my opinion, this is the most exciting discovery we've had yet with Spitzer in its almost 14 years of operation. As you can see in the graphic, the initial discovery of the TRAPPIST-1 system was by the TRAPPIST telescope in Chile in 2016. And immediately after that, we started doing intensive follow-up with a lot of ground-based telescopes and more than 20 days of continuous observations with Spitzer. And what we're able to find is that we confirmed 2 of the planets that were found in the initial discovery, and then found 5 more planets for a total of 7 planets in the system, which is pretty exciting. Now, TRAPPIST-1 is an ultra-cool dwarf, and that means that it's much brighter in the infrared, thousands of times brighter in the infrared than in the visible. So it makes it ideal to use Spitzer, which is an infrared telescope, to do the follow-up on this system. And then as you can see in this animation of Spitzer, so Spitzer was launched in 2003, and it was never intended to study exoplanets. So we had to do some clever re-engineering why it's in space still, and it's more than an astronomical unit away from the Earth, so you can't fly out and do anything about it. But we did clever engineering on the ground to come up, allow Spitzer to measure star brightnesses very precisely, 1,000 times more precisely than we had imagined Spitzer would be able to do. And then what we're going to show in the next animation is how what Spitzer sees the planets very similar to the way the Kepler Space Telescope does. We don't image the individual planets. What we do is the planets pass in front of the star. We see the amount of light that the star is dimmed by when that planet is blocking it. So the dips you see in this animation are the planets going in front of the star, blocking a little bit of the light. The size of the dip tells you the size of the planet. So we can get the size of the planet directly from measuring the dip. Now, when you see the different planets, they keep orbiting around, and every time they transit, you can measure the spacing between the transits, and that tells you about the orbit, the period of the orbit, how long that year is, and for that planet. And then when we know how long it takes for the planet to go around the star, we also know the distance it is from the star, and that also tells us whether or not it's in the habitable zone. Now, the TRAPPIST-1 system and its planets are in an interesting configuration. The planets are all very close together, and their orbits are spaced such that they gravitationally interact with each other. They tug and pull each other as they go flying around, orbiting around their star. And what that does is it changes the timing of the transits a little bit as the planets are tugging each other, so they don't happen as regularly as you would expect without the tug. And with that, measuring those differences, what we're able to do is measure the masses of the planet. So now we have the mass of the planet, the size of the planet, so we can make an estimate of what the density of the planet is. And that's important because that gives us some understanding about what the composition of the planet is. From that, we can tell where the planets are, whether they're rocky, gaseous, or even watery.
The innermost planet in the habitable zone is TRAPPIST-1e. So in this illustration, you'll see an artist's rendition of TRAPPIST-1e, which is a really interesting planet for a number of reasons. It's very close in size to Earth, as you can see here. It also receives about the same amount of light as Earth does in our own solar system. This means that in TRAPPIST-1e, you could have temperatures that are very, very similar to the ones that we have here on Earth. The next planet out is TRAPPIST-1f. Now, this is a potentially water-rich world that is, again, about the same size as Earth. You can see here in comparison. Now, TRAPPIST-1f has about a 9-day orbit, and during that time it receives about the same amount of sunlight as Mars does in our own solar system. And the final planet in the habitable zone of the TRAPPIST-1 system is TRAPPIST-1g. Now, TRAPPIST-1g is the largest planet in the TRAPPIST-1 system. It's about 13% larger radius than that of Earth, as you can see in this comparison here. And it receives about the same amount of starlight as somewhere in between Mars and the asteroid belt in our own solar system.
So in addition to the speculoos, in astronomy, when someone makes a discovery like this, we put almost any telescope that can follow up. And so in that way, we have, we heard about Hubble already from Nicole, but the Hubble, Kepler K2, Spitzer, and other telescopes are exploring the TRAPPIST system further. I'd say that what the team is most excited about, although this is still a bit in the future, is the James Webb Space Telescope, which will launch later in 2018. Because with this telescope, and the reason the TRAPPIST planets are so significant, is that they are accessible to observations with the James Webb Space Telescope. You can see an animation of it here. So with the James Webb, we'll be able to study the atmospheres, and we will try to assess the greenhouse gas content, which will help us understand the surface temperature of the planets. Are they indeed the right temperature to support liquid water and life as we know it? In fact, we're even going to use the James Webb to search for gases that don't belong that might be produced by life, such as oxygen, ozone, methane, and a whole host of other gases.